Hi there. In today's lecture, we're going to be doing some revision on optimization for your final test that's coming up on the 16th of November. Okay, so just to recall what we mean by optimization. So let's say we have some function f of x, and we would like to find the local minimum or local maximum, or the global minimum or global maximum, depending on what's asked. So sometimes we want to find the minimum, so we're looking for this point over here, where that is a turning point at the bottom, or we're looking for a maximum where we've got the turning point at the top. In both cases, we know that the tangent line will be horizontal, so it's horizontal at the minimum and horizontal at the maximum. So in terms of derivatives, we know that a local min or local max occurs when f prime x is equal to 0. In other words, you have a horizontal tangent line. So whenever you have to optimize something, whether it's minimize or maximize, your first step is always determine what your function f looks like, so the thing that needs to be maximized or minimized, and then your next step is to take the derivative and set it to 0. Okay, so in both cases, we want to do that. Okay, so let's just go through a few examples. So very similar to the ones that we've seen this semester, and very similar to the ones coming up in the final test. Okay, so number 1. Given two numbers x and y, such that x plus y equals 8. So we've got a restriction on these two numbers. Determine the values of x and y that give a maximum product. Okay, so what does this mean? We've got this function, the product of the two, let's call it p, that's equal to x times y, that's the product of the two, and we want to maximize it. So we want to have p prime equals 0. But here we've got two variables, x and y, so we can't take the derivative with respect to x because we have two independent variables. So what we want to do is eliminate one of them so that we get back to our single variable calculus. So how do we eliminate one of them? Well, we can use this constraint that's given to us. So we know that x plus y is equal to 8, so y is equal to 8 minus x. Or you could have solved for x and written this in terms of y. Both will give you the same answer. So here we can now write p of x, so it's a single variable function now, is x times 8 minus x, which stands in the place of y. So we can multiply this through, so we get p of x is 8x minus x squared. Okay, simple quadratic polynomial. We can now take the derivative and set it to 0. So p prime, that will be 8 minus 2x, and we want that to be 0. So 2x must be equal to 8, so x must equal 4. And if x is 4, we can go back to our equation for y over there. So y is 8 minus x, so y is also equal to 4. So the sum will be 4 plus 4, which is 8, so that satisfies the constraint, and the product will then be 16. So p max will be 16. So we have x, y, as well as the maximum product. Okay, for the next 4 examples, we're going to look at the more geometric picture of minimizing or maximizing some area given a constraint. Okay, so let's look at number 2. Okay, we've got a unit circle, so radius is 1. Inside we draw this rectangle, so it's above the x-axis but below the top semicircle. and we want to maximize this area here. Okay, so to set up the problem, we need a bit of variables. So let's call this base point over here x. So from the origin to x, that's going to be half the base, right? Because if x is on the right, you're going to have minus x on the left, and then together that will give you the full base length of 2x. Okay, what about the height? The height is going to be the function value at that point. So what is the function value? Well, we know for a unit circle, x squared plus y squared must be 1. So y squared is 1 minus x squared. So y is the root of 1 minus x squared. Now here we don't take plus or minus the root because we're looking at the upper semicircle, so y must then be positive. If we were looking at the lower semicircle, then we would take y equals minus the root. Okay, and this is therefore our height of the rectangle. So the base is 2x, like I explained before, and the height is the root of 1 minus x squared. So the area, let's call it A, is going to be the base, which is 2x, and the height, which is root 1 minus x squared. Okay, I saw a lot of you were putting the base as x for the class test. I still gave you the marks because that does give you the right answer for x, but it will give you the wrong answer for the area. The area is 2x, okay, times the height. Okay, so if the question is asking for the area, please make sure that you have your dimensions correct. So here the base would then be 2x, not just x. Okay, so let's take the derivative. So a prime, we can take the derivative of the first function, leave the second one alone, plus we leave the first one alone, take the derivative of the second, so we end up with minus x over the root 1 minus x squared, after cancelling the 2 from the chain rule with the 2. That should be at the bottom when we take the half down. Okay, and then this must be equal to 0. Now the 2's on both terms, that can go, so we can write this as root 1 minus x squared minus x squared over root 1 minus x squared is equal to 0. Now these roots are in the way, so let's multiply the left-hand side and the right-hand side by the square root of 1 minus x squared. Okay, so the right-hand side stays 0, we don't need to worry about that, but this left-hand side becomes 1 minus x squared minus x squared. Okay, so this is going to be 1 minus 2x squared is equal to 0, 2x squared is 1, so x is 1 over root 2. Again, we take the positive x because from our diagram, this x is on the right-hand side, which means it's positive. The other base point on the left-hand side, that would then be minus 1 over root 2. Okay, so we've got our x value. We can then find the y value. So that's going to be the root of 1 minus this x value squared. So that's root 1 minus a half, which is root a half or 1 over root 2. So we have x is 1 over root 2, y is 1 over root 2. So then we can then find the area, which is 2x times y. Remember, the base length is twice x because x only measures half that bottom width. Okay, so this is going to be 2 times 1 over root 2 times 1 over root 2. That's 2 times a half, so that's just 1. So we have our x value, we have our y value, and we have our correct area with this 2 in front to take into account that base width. Okay, let's have a look at another one. Number 3. So here we've got ourselves a straight line given by y equals ax plus b. And notice from the line that this a will then be negative because it's a downward sloping line. Okay, and we've got this inscribed rectangle over here. again with this little base point here being x and the height being y, given that x value. Okay, so what we want to do is find the area or the maximum area of this inscribed rectangle. Okay, so we write down an area function a. That's going to be base times height, so that's going to be x times y. But we know y, given that x value, it's going to be this point on the line here. So it's going to be ax plus b. Okay, so that is our area function. Now what we want to do is maximize. If we wanted to minimize, we would do the same thing, and that is take the derivative. So a prime, that's going to be d by dx of, let's multiply this out, ax squared plus bx, or you could have done the product rule. Multiplying out is a bit easier. So this is going to be 2ax plus b, and we want that to be 0. So minus b is equal to 2ax, x is equal to minus b over 2a. Okay, so this minus, that might worry you because here we said x was negative, but that's not a problem because we said at the beginning that a was negative because it's a downward sloping line. So if b is positive and a is negative, we've got a negative and a negative, so that makes x positive again. So in fact, this is a positive number like we wanted. Okay, so that's the x value. The y value would then be, like we had here, ax plus b, so we multiply through by a. So you can have a times minus b over 2a plus b. So y is equal to minus 1/2 b plus b, and that's just 1/2 b. Okay, so we've got the x value, we've got the y value. We can then find the area, which is x times y. So the area is x times y, so it's minus b over 2a times 1/2 b. So that is b squared over minus 4a. And again, this is a positive area because we know that a is negative because it's a downward sloping line. Okay, so just because there's a minus sign in front doesn't mean that it's a negative area. It is still positive. Okay, let's have a look at another one that's similar to this, but instead of a straight line, we have a parabola. Okay, so very similar to what was in the class test. Okay, and similar to what will be in the final test. So here we've got a parabola. Y is equal to a minus bx squared. So sad face parabola because the coefficient of x squared is negative. So here a is positive, b is positive, but since it's minus bx squared, again it's sad face. Okay, so we've got our inscribed rectangle with some base point there, x. So if that's x, the other side is minus x, and so the total width is 2x. Okay, so what's the area? The area is going to be base times height, so it's going to be 2x times the height. The height is the function value, so that's a minus bx squared. Okay, let's multiply this out. So we get 2ax minus 2bx cubed. Okay, now we can take the derivative and set it to 0. So a prime will be 2a minus 6bx squared, and this must be 0. Okay, rearranging, we get 6bx squared is equal to 2a. So 3bx squared is equal to a. So x is equal to the root of a over 3b. Okay, and this is going to be positive, which is what we wanted, because the x value is on the right-hand side where it is positive. Okay, so that is the x value. What is the y value? So we can just substitute. So y is equal to a minus bx squared. So that's going to be a minus b times a over 3b, just by multiplying the x with itself. So that gets rid of the roots. So the b's can cancel. So we have a minus a over 3. So we're left with 2/3 A. So that's the y value. We've got the x value. So multiplying y with 2x, that gives us the area. So the area is going to be 2xy. Okay, so that's going to be 2 times x, so that was root a over 3b, times y, and that was 2/3 a. Okay, so you can simplify that if you want, but I'm just going to leave it like that as the area for that rectangle. Okay, last one to go through, number 5. Okay, same idea as before. We've got some shape, and below that we've got an inscribed rectangle, which we want to have a maximum area. So in this case, the curve or the function is given by sine x. Okay, and we've got our inscribed rectangle here with base point A, that's given by x0, and then we've got the other base point there, B, and we don't know what that is yet. Okay, and of course that's 0 pi, 2 pi. Okay, so we want to maximize this. Now we've got the first base point here at x, that's what we need to solve for, but we don't know b. But we can work it out quite easily just from symmetry, because if this distance here is x, then the distance from b to the next x-intercept there, that must also be x, right? Because it's symmetric about x equals pi over 2. So if we know what a is, we know what b is. Okay, so we know this bit here is x, this bit here is x, so this bit in the middle will then be pi minus 2x, because from 0 to pi, that gives us the full length. We're taking away x on both sides, so this middle bit must be pi minus 2x. Okay, so that's the base. Okay, and then the height, that's the function value at x, or at a, or the function at b. It's the same, right? Because this top line must be parallel to this bottom line for it to be a rectangle. Okay, so the height is sine x, and the base is 2 pi minus, pi minus 2x. So base, pi minus 2x, and height, that must be sine x. Okay, so that means the area is the product of these two. So A will be base times height, so pi minus 2x times sine x. We can multiply this out, so we get pi sine x minus 2x sine x. Okay, notice we've got x times sine x, so we're going to have to use the product rule there. So A prime, that's going to be pi cosine x minus 2 sine x minus 2x cos x. Okay, so that's using the product rule with x and with sine x. Now we want this to be equal to 0. So 0 is equal to pi cos x minus 2 sine x minus 2x cos x. Okay. Now we've got two cos terms, we can put those together. So that's going to be pi minus 2x cos x minus 2 sine x. Okay, we can take the sine x over, so we get 2 sine x is equal to pi minus 2x cos x. Okay, we can divide through by cos x, so we get 2 tan x, right? Sine over cos is tan, is equal to pi minus 2x. Okay, now this is a so-called transcendental equation. You don't need to worry about the name, but this cannot be solved so easily. Okay, instead we would resort to plotting these two and approximating the intersection point. Okay, however, for this question, this is all we wanted. Okay, we wanted to show that this x value satisfies this equation here. Now you can plot these two on Desmos and see where they intersect. That would give you an approximate answer. but we don't need to go further with this. Okay, so that's going to be all the revision for today. If you have any questions on this optimization, please just email me, or you can email the tutors. Okay, they're quite happy to help you. If you have any further questions about the final test, again, the information is on the Learn page, but you can email me as well. Okay, so remember, the scope for the final test is everything. So there is a couple questions, on a few things that we have done this semester. Okay, if you go through your class test 1, your class test 2, and the tutorial questions, then you will be more than fine to write the final test. Okay, so there's nothing new being added. It will be exactly the same as the questions that you've seen before. Okay, so please just revise that. Okay, but if you do have any questions while you're going through your work, please don't hesitate to email me, or you can meet me in my office, but that will be not this week, for the week of the, so from the 24th of October onwards, I'm going to be away, so the week after, then you can come to my office. Okay, but please email me if you need to. Okay, so I'll see you in the following week.